So this lecture on motion in two dimensions is a crucially important lecture. We've dealt with the use of the Newtonian equations in one dimension. That's something maybe falling directly up and down, or moving right and left, or east-west, north-south, but not something moving maybe up and to the right, or east and south. When we have motion in two dimensions, the use of or our understanding of vectors is much more important. So you'll also find that these are more realistic type problems. And when you get into your grade 12 physics course, your understanding of motion in two dimensions is going to be crucial, because a lot of the solutions to problems you'll have will involve things in two dimensions, all types of quantities, not just motion. So although uniform motion, as discussed earlier, is the simplest motion to analyze, it's not as common as non-uniform motion. So if we can change direction, we now have non-uniform motion, even if the speed remains constant. So for example, on a rainy day, we have a boy who walks 1.7 kilometers east of his home, then 1.2 kilometers south to get to a skating arena. On a clear day, he can walk straight across a vacant field to get there. So in both cases, his resultant displacement is the same, whether he travels the 1.7 kilometers east, then 1.2 kilometers south, or if he travels directly across the field. His resultant displacement is the same. In this case, it would be 2.1 kilometers, 35 degrees south of the direction east. So as we mentioned earlier, we'll not use a scale diagram because that's very time consuming. Instead, you can sketch the vector diagram to help you understand the motion, and then you can use your understanding of Pythagorean theorem and trigonometry to determine the length of that resultant vector. So in this case, you can find the resultant displacement by finding the square root of the square of 1.7 plus the square of 1.2. And you can find the angle by looking at what we have here. The tan of 35 would be 1.2 over 1.7. So the angle is equal to the inverse tangent, the inverse tangent of 1.2 over 1.7. Here's another problem. We have a cyclist going 5 kilometers east, 4 kilometers south, and 8 kilometers west. This is the vector diagram. We used this in a previous lecture, and this shows the displacement, the resultant displacement. So just as for one-dimensional motion, for average velocity for two-dimensional motion, the average velocity for two-dimensional motion is the ratio of the displacement to the elapsed time. Since more than one displacement may be involved, the average velocity is described using the resultant displacement. All right, now here's a problem we'll work out. We have a football player here. They move 8.5 meters east, 12 meters south, 13.5 meters west. So we've drawn a vector diagram of this, but what we're more interested in is the second part, where we're asked to, it says if the tire motion takes 7 seconds, how do we determine what his average velocity was? So in this case, we're going to start, and we're going to start by, just a second here. We have to look at what is his displacement in the x and the y direction. Let me move this. Maybe I can change the size of this here. Oops. So I want to have this on the screen at the same time as that. So, okay, now we can see both on the same screen. Let's first figure out what is his displacement in the x direction. So he goes 8.5 east, 13.5 west. So 13.5 minus 8.5 gets us to a total displacement of 5.0 meters in the west direction. And his displacement in the y is equal to 12 meters, 12.0 meters in the south direction. So now I have a displacement in the west and a displacement in the south. To find my resultant displacement, my delta dt, I have been dropping these arrows above, but these are all vectors. It is equal to finding the square root of my dx squared plus my delta dy. My camera not working too well. So it is equal to that, delta dx squared plus delta dy squared. That would be the square root of 5.0 squared plus 12.0 squared. And you'll find this is going to work out to a very nice solution. I'll show it to you on the calculator. 5 times 5 plus 12 times 12 is 169, and that is actually a square number, the square number for 13. So this equals 13 meters, but we don't have a direction yet. So what we have to do is a side calculation to determine the direction. So for this, I'm going to find the inverse tangent and the trick here to determine which values to use is we always use the smaller value over the larger value. So the inverse tangent of 5.0 over 12.0, and on my calculator, 5 divided by 12 is this value here, and the inverse tangent of that, oops, sorry, I actually already had it, already calculated it. 5 divided by 12, inverse tangent of that is 22.62, or we'll say 23 degrees. Now I can go back to my solution here and write my direction. 13 meters, 23 degrees. But how do I write where this is going? Well, if it's gone 12 meters south, then I'm going generally towards the south. I make a 23-degree turn towards the west, and I travel that additional 5. So when I write this down using 5, my lower value, over my larger value, my direction becomes the primary direction is the larger value. The secondary direction is the lesser value. So 13 meters south, 23 degrees west. That is my solution. Okay, let's move on. Oh, you know what? I forgot, because it does actually say what is the average velocity. I then have to just divide that by 7. I won't do that right now. You can do that yourselves. Finding the resultant displacement is the difficult part. Dividing by 7, you would end up getting 1.9, and that would be your the direction would be the same. It would still be south 23 degrees west. That's how you would find your average velocity. Another question. The student starts at the westernmost position of a circular track with a circumference of 200 meters. They run all the way around the track in 26 seconds. Assuming two significant digits determine the student's average speed. Well, if they've traveled 200 meters around a track in 26 seconds, we just divide those to get 7.7 meters per second. That's rather easy. Their average velocity, though, is dependent on their displacement over the time. So this would essentially be 0 over 26. And because 0 divided by anything is 0, then the average velocity is 0. Question 4, we have a ball rolling with an initial velocity of 40 meters per second west. It undergoes an acceleration of 5 meters per second squared north for a period of 6 seconds. What is the velocity of the ball after the 6 seconds? Well, this question we will solve using, I'm going to bring my screen back to its original size. We'll solve this using what we were using before, the Newtonian equations. So from the problem, I have an initial velocity, I have an acceleration, I have a time. I need to find the final velocity. So if I'm looking at that, I'm looking for something that has initial and final velocity, something that has time, and something that has acceleration. This is not acceleration. This doesn't include, this includes delta d. So it's going to be something like this. Final velocity, initial velocity, acceleration, time. So VF, for question 4a, VF equals VI plus AT. To bring this up here. And I need to find my final velocity, so let's start with our substituting. VI is 40 meters per second west. A is 5.0 meters per second squared north. The time is 6 seconds. I'm going to get into a little bit of a impasse here because 5 times 6 is 30. That's directed north. I can't add a west direction to a north direction. At least I can't add them directly. What I have to do is vector addition. And vector addition is when I add them using the square root of the sum of their squares, also called Pythagorean addition. So if I'm adding something that have cardinal directions that are 90 degrees away from each other, this is how you would add them. This would not be 70, and the reason why is because it wouldn't be 70 northwest. It's going to be moving at some other angle because it's moving more towards the west than it is towards the north. If they were both equal, if this was 40 and that was 40, you would still do vector addition, and you'll find out that they would actually be going northwest because the angle between them would be 45. But in this case, we have to do this vector addition, and I'll let you figure out what this is. It's going to come up to a very nice number of 50. But before I write down this here, I have to do a side calculation. The inverse tangent of the smaller value over the larger value, 30 over 40. And the inverse tangent of those, I won't show this on the calculation, but it's I'll tell you what the calculation is, what the answer is. It's going to be 37 degrees. That's my side calculation. So when I write this in, it'll be 37 degrees, but which direction am I going more towards? Am I going more towards the west or towards the north? Because this is a greater value, I'm going more towards the west. So west, 37 degrees, north. So essentially I'm going to the west, I'm making a 37 degree turn towards the north. This is what my direction would be. And that's my solution for that question. I believe there is a part B to this question. It says, what is the displacement of the ball after 6 seconds? D equals VIT plus AT squared. 0.5 AT squared. So I'd have to use this to find my displacement. VI is 40 west. T is 6.0. 0.5. My A is 5.0 north. My T is 6.0 squared. So I have to calculate these individually. 40 times 6 is going to be 240 west. And 36, let's see, that's going to be 36 times 0.5 times 5 will be 90. Again, I need to use vector addition here. And this one I'll show you because it is not going to be a nice number to solve. 240 times 240 plus 90 times 90, and the square root of that is 256. I need to solve. You're not seeing what I have because it's underneath the calculator. The inverse tangent of 90 over 240, and that's going to be, calculator, 90 divided by 240, inverse tangent, 21. I am going towards the west with a 21-degree turn towards the north. Last problem to do here. We have a car traveling 15 meters per second north. This car ends up exiting a curve at 18 meters per second east. What is the car's change in velocity? So here, the change in velocity would be, for 5, we have a delta V is the second V2 minus the V1. So the V2 is 18 east. The V1 is 15 north. Well, I'm going to change that north, negative 15 north to a south, so it's going to be 18 east plus 15 south. Now I have to do vector addition. 18 squared plus 15 squared. I can even write on the side my side calculation already. Inverse tangent of 15 over 18. And I know that it's going more towards the east, so it's going to be east in whatever direction I find for my direction there. So let's do 18 times 18 plus 15 times 15 and find the square root of that. I get 23, I'll just round it to 23 meters per second. And then my angle, 15 divided by 18, my angle is second tangent, 40 degrees. So it's going to be east 40 degrees south for that problem.